I'm Matteo. I'm a postdoc at IMDEA Software Institute, and I'm the only obstacle between you and lunch. Knowing that you're authorized, if you get too frustrated, to just grab a very large object in your range, throw it here, I'll get the message, we go at lunch. Okay? Your neighbor's laptop. All right, so I'm gonna give it a try and give a talk about design philosophy in SNARKs, and this is related to some of the work I did with Anais, who's here in this audience, and Dario, and it's going to be presented at CCS in a couple of weeks, actually. So, if I had to summarize this talk in one slide, it'd be this. We want to try and talk about SNARKs that are interesting and efficient, like complex organisms of sort. How can we make them from smaller, simpler blocks? And the composition should be as simple as possible. This is the talk. But I'm going to try and motivate this a little bit more and clarify what I mean with this. So first, just as a caveat, we're focusing on the non-interactive setting, and we care about succinct proofs. All right. Why do we care about modularity, and what do we mean with that? Let me tell you two tales. First, a tale of efficiency. The ones were a very young cryptographer who wanted to prove efficiently in zero knowledge this relation. This relation is simply, you have a bunch of bits H, and you want to check that the SHA computation of two matrices smashed together in a multiplication give you this. And he observed that this relation could be done sort of decomposed in two parts. The SHA part, which is highly Boolean in nature, and a highly algebraic matrix multiplication. And this sounds, he thought, an interesting observation. Maybe I could use it to do efficient SNARKs out of it. And there's ways to do it. However, he wasn't that lucky. He went to the local wizard, local bearded wizard, and the local bearded wizard say, look, I got two zero knowledge proofs for you. They're general purpose, and they may have what you need. One is amazing in the Boolean setting, but really bad in the algebraic setting. And the other is really bad in the Boolean setting, but marvelous in the algebraic setting. But then the cryptographic hero said, well, but then if I use ZKP1, I'm going to be bad on one of them, and the same for 0KP2. This looks suboptimal, he cried in frustration. And he was never able to prove his relation efficiently. He abandoned cryptography and became a divorce lawyer in New York City and lived happily ever after. Now, this is a happy ending, but being at Zero Knowledge Proof Workshop, we care about a different type of ending, happy ending at least. So the obvious question is, why can't we get the best of both worlds? Why do we need to choose in this sense? Can we just, use ZKP1 for the Boolean part and ZKP2 for the other one? And this can be done, but it's not that trivial. I mean, these, for example, they share an intermediate state, the Y intuitively, and it's a zero knowledge proof. We need to be careful in how we decompose this. So let's see how we can get happy. And notice that these splittable relations are common. If you think of databases, like you do a select query and then you aggregate something, two parts, two different nature of computation. And a polynomial evaluation, like first you compute all the coefficients of the powers, and then you do an inner product with the coefficient. Second tale, a tale of simplicity. The ones were two bearded wizards. Who knows who these two bearded wizards are? Okay, so they are Brian Kernighan and Dennis Ritchie, authors of UNIX, that just turned 50, by the way. And I want to talk a little bit about, just one slide, about UNIX simplicity. Who's familiar somehow with UNIX command line in this audience? Okay, good, very good. Nice. In UNIX, one of the reasons there is simplicity in a sense is that we have shell commands that are very simple. They do one thing, and it's pretty simple. Grab, filters text, sort, source it out, and so on and so forth. So one corollary of this is that at times you don't need to write entire programs to solve complex tasks. You just glue programs, among these ones, say, to solve the complex task. So for example, suppose you want to solve this problem. You have a digital phone book of sort, and you want to find the top 5 most frequent first names. So we care about the second field over here. Instead of writing a new program, just do this. You just glue them together in a pipeline. Use the pipeline that sort of passes the output of one program to the next. Can we be a little bit more like Unix in the SNARK world? So what's the UNIX philosophy? Write programs that do one thing and do it well, and make them work together. And in order to do that, they need to handle, in the Unix case, text streams, which is a pretty simple and universal interface. How can we export this philosophy in our context? Let's write SNARKs that do one thing, do well and fast. They should be able to work together, of course, and they should be able to handle a universal ZK interface, which are commitments. If you don't know what a commitment is, I'll get there in a second, just ignore this. I'm anticipating things. What allows us to make programs work together in Unix? The pipeline. The pipeline shares text from one process to the next. So what we need is sort of a zero-knowledge cryptographic pipeline. This pipeline needs to preserve soundness, zero-knowledge, succinctness in our case, and so on and so forth. Right. And the spoiler I just gave is that the pipeline is going to handle commitments. So we're going to call it commit and prove approach. Pretty simple. Commitments. Please raise your hands if you are somehow familiar with commitments. That's pretty good. That's fantastic. Commitment allows you to take an input U and close it into a sealed envelope of sort. And what we care in zero-knowledge is that it's hiding. I don't know what's in the envelope. And most importantly, that it's binding. So if I give you the envelope, it can be opened only in one way. Now, what's a commit and prove SNARK? In a commit and prove, in normal SNARK, you have a relation, RU, takes an input U. And if I prove it to you, I know that the relation R holds for some input U. Let's assume it's a existence sort of statement for simplicity. In a commit and prove SNARK, we have a commitment to U as an interface of sort. This is a rough approximation of what things are, because there's no real distinction between the two, but we can think of them this way. And if I give you a proof in a commit and prove SNARK, what I know is that there is a relation R that holds for what is inside the little envelope. Why do we care about the envelope then? Well, let's look at the verification interface now. Now I can use the commitment, the envelope, as a token to know, oh yeah, whatever is inside here, I know that the property that pi gives me holds for it. How do we use it? Warm-up question. If I give you a sealed envelope to something, and then two proofs, pi1 and pi2, for two properties possibly, no, spoiler, never mind. All right.
I think it still has a question.
All right, but so if I give you a sealed envelope, two different proofs about the same sealed envelope, what do we know? We do know that whatever is inside the sealed envelope, well, the two properties hold for the same. This may sound trivial, but it comes from the binding property. It's not like it holds for anything, right? How do we use it? Let's get there. Let's get back to the relation, the cryptography here of becoming a divorce lawyer wanted to prove. So it's this one, right? We have a shell computation on top and a matrix multiplication. What's the state they share, once again? The state they share is the white thing. So this is the thing we need to be careful about. So we can split it in two parts, like autonomous shell computation that takes the input H, could be private or not, and a commitment to Y. And then we have another relation, which is commit and prove. So it takes an input this Y here, and the A and B. What can we do with it now? Well, let's assume we have two efficient zero-knowledge proofs. One is efficient for this, one is efficient for this. And we make a proof for the first one, a proof for the second one, and then I give you the commitment to Y. So this is zero-knowledge because Y is hidden, H is hidden by the proof here. Y is hidden by the commitment, if the commitment is hiding. And similarly here. Now, at the price, I can now have the best of both worlds at the small price of a constant succeedance loss. So I have 2 proofs instead of 1. If they're succinct though, if each of them is less than a kilobyte, I have a little more. And of course, verification is just the conjunction of the 2. Now, a nice interesting application of this, and this slide is also to clarify what we need from the particular approach of commit and prove I'm talking about, is the following. Let's assume there is a blockchain, and then we can post things on it. For example, your bank maybe one day comes to you and says, hey, here's your credit history. I'm going to post it on the blockchain and sign it inside the commitment, so it's in there. And now you can go to any third party and say, look, there's this credit history in the sky, and it's signed by my bank, and the opening inside has certain features, a certain property. The interesting thing is that the bank doesn't need to know what you're going to prove tomorrow about that's what we want. We want that the bank needs to be able to commit today to things you don't know what you're going to prove tomorrow. So I want to be able to commit, put in the envelope, I don't care what you're going to do with it, just compute the average of your credit history, like a statistical mean or something, or another function, don't care. And this is what we like to have. This is useful in a bunch of places. But it requires the commitment, the envelope here, to be completely decoupled from the proof system. But this is not the case, trivially. Like in many systems, in the state of the art, that's necessarily not the case. All right, so what did we see so far? We saw that we want to be more like UNIX, to be efficient and clean and beautiful, and we want to be able to compose NARCs using commitments as a glue. But then what's next? So if we want to be more like UNIX, I'm going to talk a little bit about how to build the small atomic processes, commands, building blocks you want to work on, and the challenges of doing that. Then I'd like to see, all right, that this is really cute, but can we use it for anything real? Is this really efficient? Can we do complex stuff with it? Or are we going to stay at the Lego level all the time? And finally, I'm just going to mention a little bit about the LegoSNARK library and its philosophy. Go with time. Vanilla pool of gadgets. All right, so what alternatives do we have what possibilities do we have to build initial gadgets? Well, as a start, it's 2019. That means there's been a lot, as you guys are aware, a lot of research about SNARKs. Should I just come with a new paper and say, forget about, or you said, no. Let's try and import what's already out there, right? And we're going to see, and also there's a lot of general purpose systems. We don't need to have specialized systems necessarily. Next, of course, we do want to have some specialized new CP SNARKs. Let's talk about this first. How do we do it? So there's a bunch of these works, and we'd like them to be here. Well, there's 2 challenges. First, they are not efficiently commit and prove. You can make anything trivially commit and prove, but efficiently commit and prove is tricky. Is this really a limitation, right? I can take any of this system and say, prove to me that R of U holds, and also that it opens to a certain commitment. At times, this is going to get very expensive, almost all the time, if you do that trivially. Zcash does it, and it does it beautifully, but it does it with very specialized parameters. So what you're losing is simply the universality of it. There is other CP SNARKs out there, but they're CP in a weaker sense. They cannot talk to each other. They deal with different commitment schemes or keys. And we need to have a universal pipeline or glue of sort. So we need to solve the problem anyway. So these are the challenges.
Does your definition of CP SNARK encompass the other CP SNARKs?
No, maybe not. Because, for example, the commitment key say take Geppetto. Geppetto commitment key depends on the set of relations you want to prove. So before knowing the commitment key, the commitment scheme depends on what you want to prove.
So it's not really like separated.
No. And of course, it depends on all the QAP framework that Geppetto uses.
Sure.
Sure.
commitment need to be homomorphic for some reason?
It does. It comes handy in a bunch of situations, but it doesn't in principle.
So in cycling, for example, we use a homomorphic commitment for the values. We're essentially doing this, but with the same proof system between the spend and output proofs. So that means that we can just add up the inputs, compare them to the outputs. And that works because it's homomorphic.
All right, so this is the only slightly technical slide. Please ignore it if you don't care. How do we compile ZK-SNARKs into CP-SNARKs? So very high level, really, actually. We just observed that many of these schemes over here, they share a common property that we call, they're CC-SNARKs. They're commit carrying SNARKs. A new notion of SNARK that simply says the following, that you get a proof out of that system, but also a little very specialized commitment. What we then do, we build a compiler from CC-SNARKs, from all of those that satisfy this property, to efficient CP-SNARKs. To do that, we first populate this framework with a specialized commit and proof gadget that does the following. So there is two commitments, two envelopes in two different schemes or keys. They're Petersen commitments. It links them together efficiently. And now what you can do is just merge these two guys together. So I prove to you with this scheme that our review holds. I get a proof, I get a specialized commitment, and then I can use the commitment linking to sort of link it to a universal commitment of sort that doesn't depend on the keys and the relation or anything. That's it. And as a consequence, we can make commit and prove efficient version of Groth16, Geppetto, Ligma, and so on and so forth. Okay, that's for general purpose schemes. How can we reuse what's already out there? What else is new though? And well, in LegoSNARK we have, for example, efficient CP gadget for linear properties. You get a matrix, and a vector, and you want to compare to something. Matrix multiplication, Hadamard product, self-remutation. You have a vector, and you want to check if there are some patterns in it. Now, they are cute and boring and abstract here. I'm going to show you in a couple of slides that they can be really useful together. And of course, the commitment linking scheme, which is very versatile, is the one we used in the previous slide. Is this really any good? Let's check the promises of all this modularity talk. Can we glue new complex SNARKs from this? And is any of this really efficient? Okay, so some of the interesting things we stumble upon doing this are new general purpose commit and prove SNARKs. In particular, as I mentioned, simply a commit and prove version of Groth16. So now you can have efficient commit ahead of time proof for any relation of sort, in principle. And one of the first CP-SNARKs with universal structure reference string, this was actually concurrent to the Sonic work. This is linear SRS, linear proving time, with the caveat of log squared proofs. And the very interesting thing, how do you build such a system? How complex is it? Well, you just smash together Hadamard gadget and a self-remutation gadget. That's when the glue comes useful, like just the UNIX pipeline thing. Get a universal system out of these two gadgets, linking them together. All right, next, efficiency. Well, are specialized gadgets better? Groth16 is an amazing system, for example. There's others, hierarchs, and so on and so forth. And they got their pros and cons. They're really good for large classical computations. Can a specialized gadget be better? Well, at times, yes. We found this out with the matrix multiplication gadget in particular, which, for example, in concrete times, can prove to be 10 orders of magnitude faster in proving time than Groth16. And this comes from the asymptotics mostly. Our gadget is optimal asymptotics and squared as much as the input size, basically. Verification time is also pretty good, although the asymptotics tend to grow a little slower. Grow 16s times are better for smaller matrices, but then they tend to get slower. Okay, so efficiency too in some situation. So far we talk about what seems to be, what tries and be a design framework in theory. So do you design new snarks in general, in theory and so on? Can any of this be used in practice? What changes when you program this type of stuff? So in many snark APIs, a first-class citizen is the constraint system, or the wire, or the constraint itself. And this is good and useful and relevant, and that's exactly what we want. The focus in LegoSNARK is a little different. You get these objects, these gadgets, and first, they may be opaque. So the matrix multiplication gadget may not have wires inside. I don't know how it works, right? And also, what else? What else is different? The composition is a first-class citizen, and composition is sort of typed. In which way? If I have two relations, but one has a committed input and one doesn't, I cannot compose them. If I want to have a commit and prove approach type of composition, if I want to use it very often, I want to be able to check what's good and what isn't. And maybe my my programming tools should be able to allow me that. So the goals of a LegoSNARK library were sort of being any DSL, an embedded design domain-specific language for composables, CP snarks. The goal was to have abstractions for gadgets and relations, and strong typing. These allowed a bunch of template metaprogramming in C++. At the time, I thought the only language I was familiar with, it would be easy to do, would be something like Haskell. But of course, C++ was way more interesting. And oh, I don't know how much time is passing. How's it going?
5 plus a couple of questions.
That sounds good. Very good. And of course, like, I mean, if you want, what's the good of this stuff? You want to have two gadgets and you want to say, look, I have a Hadamard gadget and a self-permutation gadget, smash them together in one line of code, and now have a universal SRS of sort. And of course, it should be easy to define new stuff. I want to give some code samples about this that is a work in progress anyway. So suppose you want to define a syntax for this type of relation, and you want this input to be public and this to be committed. I'm avoiding some tiny boilerplate code, but you simply give a name, define a type. This is a field vector. This is a matrix of fields. And the first is public and the second is committed. What's interesting is that there's no macros here. And these two guys are gonna, I'm creating under the hood somewhere, this SHA-R instance, a sort of a heterogeneous structure of sort. This H is gonna, this wire is gonna be of a different type of this wire, let's say, under the hood. Yes, no? No? I saw confusion in your face and that was a good feedback. You were confused. You were not confused. Okay. I don't believe you, but it's fine. That makes sense? All right. And this allows, I mean, the goal is to have some compile time checks when we can, as much as we can. Like, for example, only with the lines sort of from the previous slide, we already have, I can define inputs. I don't need to think about, my goal as a programmer in this case was to have, I don't need to think about wires. I want to think about the business domain objects. A matrix, a vector, which are not that domain businessy anyway. But if a polynomial is a polynomial, I want to call it a polynomial. And I want my snarks to be aware of that. And my snarks will be aware of that. Because this commitment are also typed. A commitment to a matrix is different a commitment to a vector, and is different to a commitment to polynomials. Why? Because I will be using different schemes for them to be efficient. It's not just a commitment. This needs to be reflected. So for example here, I can just assign some matrix here to my field y, and if I had a line like this where I send something else, my compiler will warn me. Whenever this is possible, I mean, this should be const probably for this to work. And similarly, for my proof system, I should be able to use my proof system in a safe way. If I try and prove something where something is not initialized, we haven't initialized age, it'd be nice to get a warning. This is not going to work, but then as soon as I initialize, I'll let this work. Composition. Suppose you have two gadgets, one for this and one for this, and you want to be the cryptography here at the beginning of the story. How would it be nice to do it? Well, just call the new compose gadget type this. And in some cases you can get automatic type and merge deduction. In some cases you can't, or you can help it in some. But then you're ready to go. You have an instance for one and an instance for the other. You merge them together, so you have something of the type H commitment to Y, the other AB commitment to Y. You should be able to merge them together. That's it. Wrapping up, we saw a modular approach to SNARK designs, blocks that can be used together. We can compose them for fun and profit and get very efficient SNARK. We saw a very efficient matrix multiplication gadget, as well as the universal SRS CP. And then I showed a little API, which is sort of try to embed this philosophy. And for example, referring to your previous talk, the one about ZK interface, this is not trying to be, this is yet another programming library for SNARKs, right? It's not trying to be competitive, alternative, or even too parallel to ZK interface. It'd be interesting to know how they can be merged. It's simply, however, the focus is clearly different at this stage. And I wanted to play with I say I a lot. It is, I was curious about if this is interesting at all. This library could be out there, and we find out we don't care as a community about this type of approach, and it's fine.
There is people already wanting to use Lego Growth 16. So.
Okay, for the least. And yeah, extensions of this, I know you talked about it yesterday. Recent work with Daniel, Dario, and Dimitris Kolonellos. You can find it here. First, thank you very much for your attention. Anyway.
Thank you, Matteo. Any questions?
Yes.
Do you know of any work on trying to define CP-SNARK variants of some of the more recent proof systems, like the Sonic-derived ones?
No, I'm not aware of it.
Any more questions? No? Okay, let's thank Matteo once again.
Thank you.